So why don't we try and read as much as we can of this paper? So this is chapter 15. It's only about 40 pages long on my version of the book. So it's not a very long one. But if we say go on until about 45 minutes past, actually we'll go 50 minutes past, 50 minutes past. We'll just read as much as we can. And if we manage to do all of it, we'll just get a second chance to do it at the weekend, get a different perspective on it, I guess. But it might be that we don't manage to finish it all. But yeah, let's just do as much as we can.
Yeah, sounds good to me.
Okay, so speak to you in a bit, guys.
All right, 10 to 7, yeah?
Yeah, that's right, yeah, 6:50,
okay,
yeah.
Cool.
All right. Okay,
Cheers.
bye. Oh, hey guys.
Yeah.
Yeah, I think I was a bit too optimistic. There's actually quite a lot in this chapter.
Yeah. I was just
I all
thinking, I didn't even finish the RNN, so I thought maybe I'll just keep mum.
yeah, I think I got to the forecasting several steps ahead. But yeah, I mean, um, yeah, we might have to listen to what some of those guys have done because they might know more about RNN than I do because I know the kind of the basics, but this guy's gone through some quite interesting uses for them. But yeah, anyway,
Yeah.
I guess we'll begin.
Sure.
So yeah, starting at the beginning. So recurrent neural networks look very much like feed-forward neural networks, except it also has connections pointing backward. So that doesn't really make any sense to anything. And so this process is called unrolling the network through time. It's the same recurrent neural network represented once per time step. Okay, so all of that is a little bit abstract. It probably helps to look at an actual image of what's actually going on. So this is a recurrent neural network neuron. And the idea is that at, let's say at time zero, you're given a certain input to it, say the first entry in your time series. It uses a hidden state, which initially is set to 0. And so the input and the hidden state is used to compute an output and the next hidden state. And if you unroll it over time, so this is the same neuron now being, the same one being shown multiple times. So for instance, at this time, it was the data from this point at t-3 and the previous hidden state that went as input. It generated a certain output, and then its hidden state was fed back through into it because it's the same neuron, but at the next step. So does that make sense? Or
So, yeah, so basically the output of each step is the two outputs. One is the output and one is the hidden stage.
Yes. In
So,
the naive one, they're both the same, but they can be very different. Yes.
okay.
Because in theory, the output is a weighted computation of the input and the hidden state and a bias term that generates the output.
Okay.
And the hidden state computation is the weight vectors that are the hidden state, which is what is what you get trained on. So yeah.
And
Although I
then,
don't think I explained that well, but yes, you're quite right. Yes,
yeah,
two different outputs at each stage.
yeah, and output on each stage, we probably, I'm not sure, we are very much interested in each step. All we are interested is just to keep updating that hidden state, which keeps the information about the whatever has been input now, as well as some previous steps whatsoever.
It all depends on what you're trying to do. So if you're, for instance, forecasting a time series, then you're interested at each on the output because you're given. Let's say that the data you're given here was yesterday's data, and you're trying to predict what's going to happen today. Well, at each input, you're interested in what the model is saying is going to happen. And the hidden state, yeah, I mean that's kind of is being kept for you to help you to generate these forecasts. So you are actually interested in all of those. So this is sequence to sequence. So this is one particular example of it where you're given an input and you're interested in what the output is at that point. And then you're given the next bit of input and you want to work out what the next output is. Yeah.
Okay.
But they've got a couple of different architectures. Some where you're actually interested in every single entry on the output. Some where you're only interested in a final one and you're not so interested in the ones in the middle, but it all depends on your use case. Yeah. And then they've got a little note on the fact that this is just one particular neuron, but you could have like a whole layer of them. And the idea is that let's say you've got a vector as input here, and you're feeding that into a whole load of these recurrent units, and then they're all outputting another vector. So does that architecture make kind of sense, that you've got kind of, so the idea is that, you've got like this whole vector at each time point. So at time 0, you've got this vector that's going into all of them, and then some output, and then at time 1, you've got another vector that's going into all of them, and then another output is generated. Okay, so that's, yeah, I mean, in terms of architectures, they've got quite a few different variations, actually. So this is a little bit about the actual calculation being done for one neuron. So the input is the X, the hidden state is the Y, and the idea is that the hidden state at the next time point is the previous input times some kind of weight vector, input weight vector, plus the previous hidden state times some weight vector plus a bias term, and then some kind of activation function applied to that whole thing. And quite often it's tanh, but and in the simple example they do, it's hardwired to be tanh, but it can be something else. Yeah. And then they've got an example here where instead of individual input values, you've got actually a whole vector of input values. So this is like just a whole calculation being done in one go on a batch of input values.
Mm-hmm.
Yeah.
To be honest, I don't particularly like his choice to mix into one scene this output and hidden state. And I think that a better way to explain it is first to start with distinction between hidden state and output, to like disentangle these ideas. You can actually apply, and he eventually comes to it, that you can actually apply dense layer to the hidden state and to produce any output you want. So in this way, your hidden state dimension doesn't have to be the same as your output dimension.
Yeah,
and
yeah.
I think it makes it a bit like more confusing. It's obviously not wrong, but like I feel like more he starts where not at the beginning, but somewhere in the middle. So if you understand that this Y is a hidden state, and it can be of any dimension you choose, and then you can obviously come to the idea that if you want, your hidden state may be directly supplied to the output, but that's on like a very restricting constraint, and it doesn't have to be this way.
Yeah. Yeah, no, that's great. Yeah, that's quite right. I don't know if he was trying to simplify it, but yeah, he might have been just better off saying that. I mean, he did kind of say that the hidden state is not necessarily the same as the output, but because he started out with this simple thing, which was, whose output was kind of like the hidden state. Yeah, it kind of confused things. I know you're quite right. Okay, and then we've got. Okay, so now we come to this notion of a memory cell. And this is one way of thinking about these things is, so since the output of a recurrent neuron at each time step is a function of all the inputs from previous time steps, you could say it has a form of memory. Yeah, so if you remember this equation, that, I mean, for a moment, if you regard that as the output, that in some sense, the output at a particular time is everything that's happened, which has been accumulated by this guy from yt minus 1, as well as the current input. Then you can think of like the hidden state as some sort of a memory that it's kind of keeping. And that's why sometimes it's referred to as a memory cell. So they say, so a single recurrent neuron or a layer of recurrent neurons is a very basic cell capable of learning only short patterns, typically about 10 steps long, but this varies depending on the tasks. Yeah, so this 10 steps comes from the problem with propagating the gradients back, because beyond 10 steps, you start to have a lot of problems. And there are some slight variations on RNNs like LSTMs and GRUs, which are capable of much longer He's saying it's roughly 10 times longer. I'm not sure whether that's accurate for GRUs or LSTMs. But anyway, there are ways around that, making it into longer sequences. But you can't have them arbitrarily long, though. You still end up having problems with these gradients not being able to propagate back. I don't know if, Dinesh, have you come across this problem with vanishing gradients and exploding gradients? Have you heard of that term?
Yeah, absolutely.
Yeah, cool. So this is that problem as to why there's only 10 steps or a finite number of steps that the system can cope with.
Yeah.
Okay, so it's saying in general, a cell state at any time t denoted h of t, the h stands for hidden, is a function of some inputs at that time step and its state at the previous time step. Yeah, so here he's actually now starting to make use of the hidden state concept. Yeah, there is this notion of a simple cell, which he's kind of mentioned, where they're both the same, but they don't have to be. Okay, yeah. So this is an example of the output in the hidden state, the fact that they can be different. So now he's talking about ways that you can actually use these RNNs, and there's a number of different. Actually, it might be easier just to look at the this diagram. So RNNs can be used. So this is a simple sequence to sequence. A certain input value at a certain time generates a certain output. And you can think of this, for instance, maybe like just forecasting something or translating something, but in a very naive way, in that the output has to be matching exactly the length that the input has to match. Another variation is where you kind of ignore all the intermediate values, but only look at the last one. And that might be more interesting. Let me just go, yeah. So that might be where you're kind of doing some sort of classification. So you've taken a whole load of sequence of inputs and you're classifying it in some way. Eventually, it could be sentiment or something like that. And you've taken basically word by word or something like that as the input. And here, so this is where you're using the RNNs to actually generate data. So you're just giving it, you're kind of kicking it off with a single input. And then at each other point, you're just giving it a 0. So no additional input, but it's just using the hidden state to kind of tick over to generate data for you. So I'm not sure there's a specific example I can think of where you would do that. But yeah, this is some sort of text generation or something like that, where you're just giving it, say, a topic or something like that, and it would just start generating you some sort of sequence of text related to that topic. And then finally, you've got this more flexible architecture where you're feeding the input into this first RNN. And what it's doing is it's kind of building up a hidden state based on the inputs you've passed it. And then you're using that hidden state in a decoder, and then you're just giving that, in this particular case, he's just passing a 0, but there are ways where you could pass in the output of current as input into the next one. But yeah, an example of this would be where you're doing translation. So you've taken a sentence, say in English, it's gone through this RNN, generated some sort of hidden state for that sentence, and then the decoder will then convert that to, say, for example, German. And the two sequences now don't have to be the same length. For instance, this is only length of 2, whereas that is actually length of 3. So I don't know if anybody has any kind of questions or comments about any of these architectures.
So in the encoder part, let's say if you're doing English to French. So in the encoder part, you give the English, it creates the hidden state for you.
Yeah.
And when you go to a decoder, would you give a French? What are these zeros like?
So in a proper decoder, you'll probably do it in a different way. But in this case, the same, because an RNN always needs an input and a hidden state to do something. Here, they're always giving it just 0, and only using the hidden state to kind of drive the output.
Yeah, but in a reality, in a sense, let's say, okay, so are we saying that the the encoder has learned the input, English input, and when we go on a decoder side, it's going to just start translating it automatic. The only thing which I'm a little bit confused is, like, why would we need a decoder at all then? Why wouldn't it just start
Usually, it seems to perform better. Trying to get one network to do both of them. Remember, this is not two cells. This is just one cell, and then this is a completely different cell. It's the same cell. Unfortunately, these diagrams make it look like there's a network of 4 cells or there's a network of 5 cells, but actually it's just one. And it's just the data feeding going round and round inside it. So they're saying that basically you get better performance by not trying to convince the same thing to do multiple things. And the other issue you're going to have here is because, for instance, for translation, you're not necessarily certain that exactly the same number of tokens you're feeding on the input is going to be on the output. If it was like the one thing doing everything, then you'd have to somehow decide when to finish. I mean, let's say the French sentence was much shorter than the English. You got to keep feeding it words here, but what are you going to do with the additional words it's generating as output? Are you going to ignore those? Whereas really, and the other aspect, and I think the other reason is that if you feed it like a whole load of sentences and it builds up a hidden state, then it can actually build quite a complex structure representing that whole sentence. And then finally, that whole complex structure can be used to actually output the correct translation. So I mean, I can imagine why it would work better, because in some sense, this guy over here is kind of abstracting all the information into the hidden state about the whole sentence, because it's been fed it one token at a time. And then that whole kind of complex structure is being passed to a second guy whose job is just to output the French. Yeah, I can imagine why that would work better. It would be quite difficult for it to do both things at the same time.
Okay, yeah, makes sense.
Yeah, as I say, he confuses it by actually putting 0 here. Because in theory, the most general is actually feeding the previous back as input to the next for a decoder. Because it would make more sense to take the hidden state and the current output as being the input to the next. The hidden state is being passed through, but the output should really be passed through as well to kind of drive the output.
It is kind of passed here because of these arrows from the previous cell,
It all depends on whether that Y prime is also part of the hidden state somehow, I guess.
I think in this diagram, he wanted to keep it the most general way. And that's why it kind of can be 6-to-6 model used for translation, or can be something else. And that's why it's not like so specific.
Yeah. Okay, so sounds promising, but so the question then becomes, how do you train one of these guys? So to train an RNN, the trick is to unroll it through time, like we just did, and then simply use regular back propagations. This strategy is called back propagation through time. Yeah, so essentially it's a bit like we've unrolled it here or unrolled it here. We're going to use exactly this diagram. So for example, if I was going to train this guy, for instance, then I would have to back propagate that, and back propagate that, and back propagate all of that, because essentially I have to back propagate through all of the things that have happened in time. So that's essentially what's going to happen. So Dinesh, are you aware of this thing called back propagation through time? I think we've done it in one of the NLP.
Yeah, I am.
So it's essentially, your cost function, the partial derivatives that are against each of the outputs as each step, or however many steps you're interested in, and then you just use the gradients, all of those gradients, and just add them together into the weight matrices. And that's the back propagation. This is kind of like where you're only doing the last three. You're not doing all the the whole history, because you've got a choice how far back you want to go. And then he's saying, well, fortunately, Keras or PyTorch, whatever you're using, does this all for you automatically, so you don't have to worry about how to do this. So is that okay? I don't know if anybody had any questions about that.
So is this saying back propagation, you can stop it at any time, like not all the way back to the first?
Yes, you can always do that with most sort of, I mean, PyTorch allows you to do it, and so presumably does TensorFlow. Essentially, you choose what parameters will be modified. I mean, I think Keras will probably take it back all the way back. I don't think there's a way for you to tell it where to stop, but there's no reason why you can't tell it to stop at a certain point. Yeah.
I think there should be in hyperparameter in Keras, because you know, when your sequence gets really long, it will take just too much time to backpropagate. Like if you want to train, like to feed it a variable length sequence, then you need to define some BPTT to limit this backpropagation, because it just will become unfeasible to train.
Yeah, usually, or they might do it with the gradients are below a certain value or something like that. Stop at that point.
So because it's the same cell which is kind of like we are unrolling, so it's the same set of weights which getting updated.
It is, but the gradients will be different at each step.
At each step, the gradient would be different, but it's the same weights which getting updated on each step.
Yeah, so what they're going to do is they're going to compute the gradients for all of them and then add them all up to apply to the weight matrix. They'll apply it in one go, but they'll calculate it separately. Yeah.
So that means if you say out of 5, I want to do 3 steps, you just add 3 steps gradient.
Yes.
Okay.
And then now we get to one of the use cases, for instance, forecasting a time series. Yes, there's a little description of the forecasting problem as to whether you're there's a single value that you're trying to predict, which is univariate, multiple values per time step, which is multivariate, and missing values, which is called imputation. So there's a few different variations of things that we could be doing. Okay. And then we've got a little bit of code to generate us a time series, which is a couple of sine waves combined added with a bit of noise. So in theory, this series is perfectly predictable because it's well defined. Now, obviously, there's a little bit of noise in it, but that should be okay. So when dealing with time series and other types of sequences such as sentences, the input features are generally represented as 3D arrays of shape. There's a batch size, the number of time steps, and then the data dimensionality. Where dimensionality is 1 for univariate time series and more for multivariate. Yeah, so yeah, the dimensionality is basically how much what data we're predicting. Okay, so that makes sense. So now he's creating a training set, a validation set, and a test set from 10,000 steps. Where actually, yeah, he's creating 10,000 time series, is he? Let's have a look. Yeah, he's that many. He's creating 10,000 time series of 50 steps each. And the first, that's interesting. What's he doing here? So we've got a number of steps, frequency, series is, so 4 values, batch size with 1, and then lid space, number of steps within it. Then there's a series of random batch. Had a bit of noise. Okay, yeah. So it looks like he's taking a 10,000 time series of 50 steps each. And then the first 7,000, no, that can't be right. He must be creating 10,000 values. The first 7,000 of which are being used to train, 7 to 9,000 are used for validation, and a final 1,000 is used for test. Yeah, I'll find that a little bit confusing as to what the shape of that data is.
Different time series, it would be, we want to predict the last value from previous 50 values, and we have 10,000 of these examples of 50 steps of values, and given the first 50 steps, we want to predict the last one, and each of that sequences of 51 values is a training example.
Ah, okay, that makes sense. I was trying to wonder, yeah, for a moment there, I thought, is he really generating 10,000 time series? Okay, yeah, that makes sense.
Yeah, just it's not really like you usually have it. You usually have one time series and you slice it into like subsequent parts. But here he just creates 10,000 independent examples of time series, right?
Yeah. So baseline metrics. So here he's just using the I guess the one value from last as the so what he's doing before we start. For example, the simplest approach is predict the last value in each series as the 51st value. Okay, so this is called naive forecasting, and it is sometimes surprisingly difficult to outperform. In this case, it gives us a mean squared error of 0.02. Okay, yeah. So this is where you're kind of assuming the values actually, you're not predicting it, you're just using the last value. So another simple approach is to use a fully connected network. So you've got a shape of 50, and then finally an output of a dense layer, which is computing a single value on the output. Okay, so if we compile this model, is everybody okay with that one, with what he's doing there?
Yeah.
Yeah, so he's saying if you run it, training for 20 epochs and evaluate it, you get a mean squared error of about 0.04. So that's much better than the naive approach, okay? Because that one was 0.02 was the error. So that's about 5 times better. And then we've got a simple Area Rnn implementation. So let's see if we can beat this with a simple Rnn. So what this is taking is predicting a single output. So single Rnn with a single output. So this is the simple Rnn you can build. It just contains a single layer with a single neuron. We do not need to specify the length of the input sequences, unlike previous, since a recurrent neural network can process any number of time steps. This is why we first set the first input dimension to none. By default, the simple Rnn layer uses the hyperbolic tangent activation function. It works exactly as we foresaw earlier. The initial state h is set to 0, and it is passed to a single recurrent neuron along with the value of the first time step x0. The neuron computes a weighted sum of these values and applies the hyperbolic tangent activation function to the result, and this gives the first output y0. In a simple Rnn, this output is also the new state h0. Yeah, okay. So he's taking he's taking 50 steps of output, but only one final output is what's being generated. Does that make sense? Is everybody okay with that?
No. Where are the 50 steps?
Okay, so he's saying, so we haven't explicitly mentioned, so he's saying that we've told it, we're not telling you how much data we're going to give you. So this is where this bit is coming from, but each value is 1, yeah? So, but we're going to give it 50, yeah? And the Rnn internally already knows that it can handle any size data, and it will just apply it, that many times. Yeah, for this, and as is kind of described here, it takes the first input and 0 and then applies it. So this is actually doing a hell of a lot. Because if you give it 50 values, this is going to actually be kind of rolling it out to in theory, like a 50 time steps of the RNN.
If you give a 50 values, so 50 values will go through one RNN, and then because it's the RNN, same RNN, so that's why you're saying it's going to be 50 times the RNN.
Yeah, so it's almost internally it's going to unroll it and perform that calculation. But to us, it looks kind of really simple. And so much detail is hidden from that because, you know, the fact that it's going to apply it depending on the input shape that many times is the bit that's actually missing here, which, you know, I guess it's nice that you don't have to sort of worry about it. It might have been better if you'd actually put 50 in there to tell it, I'm going to do you 50, but I guess it's more general to say RNNs don't care how long the input shape is, you know. Yeah.
It's like at test time, you can feed any length of sequence. So
yeah.
If you're restricted to be 50, you cannot do that anymore, right?
Yes. Yeah, it says by default the recurrent layers in Keras only return the final output. To make them return one output per time step, you must set return sequences to true, as we will see. Yeah, so because we haven't done that, this is going to generate one output, which would be you know what we're interested in, which is the prediction. But sometimes we're interested in actually the output of the RNN at each time step while it's going along, rather than just the final one. And this is where this return sequences comes in handy. And says, if you then compile and fit and evaluate this model, which is just this one single RNN neuron, you'll find that the mean squared error reaches only 0.014. So it's better than the naive approach, which was 0.02, but it's not as good as the simple linear model. And then he kind of explains why that might be. So for the simple linear model, because it was like a dense layer, it had one parameter per input per time step plus a bias term. And in the simple linear model we use, that's a total of 51 parameters because we priced 50 parameters in. In contrast, for each recurrent neuron in a simple RNN, there is just one parameter per input and per hidden state dimension. In the simple RNN, that's just the number of recurrent neurons in the layer, plus a bias term. So in the simple RNN, that's just a total of 3 parameters. Yeah, so this network's only got 3 parameters in there, whereas the dense one had 51. And that's part of the reason why it didn't perform as well. And then he does this slight digression on things that you should watch out for when you're forecasting, which was kind of interesting. I must confess I don't do a lot of forecasting, but yeah, so he's saying there are many other models to forecast time series, such as weighted moving average models or autoregressive integrated moving average ARIMA models. Some of them require you to first remove the trend and seasonality. For example, if you're studying the number of active users on your website and it's growing by 10% every month, you would have to remove this trend from the time series. Once the model is trained and starts making predictions, you would have to add the trend back to the final predictions. Similarly, if you're trying to predict the amount of sunscreen lotion sold every month, you will probably observe strong seasonality since it sells well every summer or similar patterns will be repeated every year. You would have to remove this seasonality from the time series, for example, by computing the difference between the value at each time step and the value 1 year earlier. This technique is called differencing. Again, after the model is trained and makes predictions, you would have to add the seasonal pattern back to get the final predictions. When using RNNs, it is generally not necessary to do all this, but it may improve performance in some cases since the model will not have to learn the trend or the seasonality. Yeah, this is quite interesting. I didn't realize that some of these models, they required you to take trends out. You know, yeah, must be a bit of a nightmare. I mean, I know he says just subtract 1 year from the previous year, but you can't really do that if a lot of the other things have changed between the 2 years as well. So yeah, it was an interesting digression and why and how RNNs you may not need to do this because the hidden state may encode that information for you. It's not just a straight input output. There's some kind of history being kept. Yeah, interesting. I don't know if anybody had any comment on that, if you guys have got any experience.
So what he's saying is the RNN, you don't need to take out the seasonality and the trend.
He's saying that you may not need to, because the hidden state can probably encode that information. It depending how much data you have. I mean, if you know, if it's, yeah, I mean, if the data was sufficiently marked, then yeah. Although he's saying that if you do, you might get better performance.
It's interesting. Like I don't understand when you say it will encode that information, or we saying like it will ignore the trend and seasonality out of the.
Well, okay. So the whole crux of the thing here is the hidden state, and that how much information can they, because these ARIMA models and moving averages, they don't really have a lot of hidden state. At least weighted moving average is just the last n number of observations weighted in some way. And because RNNs have got a hidden state, in theory, they can have quite a bit of kind of interesting, like, information in that hidden state which they can use. Now, exactly how you convince an RNN's hidden state to take account of seasonality, well, that's probably a non-trivial problem. I mean, you'd have to have quite a lot of seasonality data. If you could tell it, for instance, what season it was and what the data was, then it might be able to somehow, in the hidden state, encode the fact that there is this seasonal trend in there. As I said, I'm not clear how much data you would need to get it to recognize that. I don't see that that's a non-trivial problem. But I can see that in theory he's saying you might, because the RNNs have a hidden state, they could encode that information, some seasonality information in there.
Automatically, okay.
But how exactly you convince them to do it now, that's a different problem. Okay, so deep RNNs now. So this is where instead of just one RNN neuron, you've actually got multiple layers of them. So in this case, for instance, you've got 3 RNNs, and you're feeding the output of one into the next and into the next. And he's saying it's quite common to stack multiple layers of cells, as shown in figure 15-7. And this is where you're unwrapping that. Then you can see the complicated flow of information that this is happening. That the hidden state is kind of feeding into the output and going into the next one. So this guy is actually getting the output and perhaps some information about the hidden state in here, which itself is updating its own hidden states. So there's a lot sort of potentially going on here, because the size of this output could be quite large. It doesn't have, I mean, the final output might be quite simple, like a single value that's being estimated, but the internal layers, the outputs could be quite a bit bigger, depending on, how things were working. Although that's my own kind of explanation on that, but the actual architecture of the hidden state is of a deep RNN, sorry, is multiple layers of these RNN units. I mean, in here he's feeding forward in time, but in theory you could have layers which are actually feeding backwards in time as well. And you will get, and some of those architectures were being used in NLP before the advent of transformers. Does that make any sense? Or I don't know if anybody's got any questions on that.
So this deep RNN is this just a layer of a different like LSTM or simple RNN. You're saying instead of one layer with the input, we're going to have 2, 3, 4 layers, and that's pretty much it.
Yes.
Okay. But would the, like, do they share the hidden state, or is it like the ones, let's say if we have 50 neurons, so it will roll and it does whatever it does, and then it will give one output, and that output goes to the next layer and it will have its own weights. get calculated. So weights are not getting shared as such between the layers.
No, they're all independent. So it's here's like an example of it here. So the first layer has got 20 neurons in it. And then there's a second layer of 20 neurons. So, so this is kind of feeding each neuron into the next one. And then finally, there's 20 of those are fed into one simple RNN, so to give you one final output. And this is where here is where the return sequences becomes important, because we've got 20 RNN, sort of this is a layer of 20 of them kind of next to each other. And then on the next layer, you've got another 20 next to each other. You have to make it that all the output from these 20 is going into those 20. So this is a way, you have to return the actual individual values that that's going to happen for those guys to be able to go into that guy. Yeah, again, I'm not explaining it very well, but does that make any kind of sense, or is that still confusing?
No, that's fine.
Well,
Yeah,
again,
I mean, it's hard to get your head around exactly what the architecture of this guy is. So it looks like there's there's 20 simple RNN units here. And then each one of those at each time step is going to generate 20 outputs. And then each one of those is going to go to another 20. And then each one of those and then this guy is taking, so that's going to return 20 again here. And then this is going to take those 20 and generate one final output. Yes, sorry, Arthur, you're going to say something. I'm trying to verbally understand what's happening.
I was going to say that it's, look, this 20 is again, I think just he didn't explain it really well, and that's caused the confusion, because this 20 is the dimensionality of the hidden state. So we can view this simple RNN like single rectangle in the diagram above as a regular fully connected network, and it takes one single input and projects it into the 20 a vector of dimensionality 20, and it will return for each input time step, it will return a vector of 20 values. And then this 50 by 20, like batch size by number of time steps by hidden dimensionality vector, is fed to the next RNN, which is again, it will then be 20 to 20 projection. Like fully, it would be like fully connected, which is repeated every time step.
Okay, and so KRS simple RNN. Oops. So let's look at the documentation for that. So, okay, so the parameter is units, and then use bias term, bias initializer, kernel regularizer, recurrent regularizer, kernel constraint, recurrent, okay, dropout, recurrent dropout, state, go backwards, stateful unroll, okay. Units, positive dimensionality of the output space. Okay, yeah. So you're saying, so that's the output.
Yeah, that's the dimension of its hidden state, which is which it outputs also.
Yeah. Okay, that makes sense. Yes. So the output of that is 20. The output of that is 20, and then the output of that is just 1. Yeah, that makes sense.
All the previous ones returned a sequence, so it returns a 50 by 20 here, and this one it like operates on all of those 50 time steps and returns only the last one, because we don't have here return sequences, and its hidden state will be one-dimensional every time, and it returns on only the last one.
Yeah, that makes sense.
So can I get this right? So input, if the input shape is 50, 50,1, and then we have the units for a simple RNN is 20. Okay, so the output of a simple RNN is going to be 50 by 20, which get fed into a second layer.
Yeah.
Yeah.
It has like batch dimension, then time step dimension, like this sequence dimension, and then it has its hidden like this hidden state dimension, you know.
Okay, and in next stage, now we had the input for 50 by 20. What's coming out of the second layer?
So that's probably the same.
50 by 20?
because it had 50. Yeah, I mean the input shape is now 20 because the dimension of the output of the previous time was 20, but there were 50 of those. And then obviously this guy is going to generate 50 times 20 again.
Okay, and that get fed into the last one.
Yeah, and then obviously that that's output is only 1 because you're only taking because you're not returning the individual 50 the sequences. You're only taking the very final output after all of those have been processed.
Okay, so all of
and
them.
Its dimension is 1 as well.
Okay, so just one single 50 by 1 will picked up, or is it 50, or is it like 1 by 20 will picked up in the end? What's the dimension of the output?
I mean, if we assume that we've only got batch size of 1, so there's only 50 values going in, one batch of 50 going in, because let's ignore batch for instance for a second. Then you got 50 values by 1. That's the time series here going in. And then because that's 50 time steps worth of data, you're going to get 50 time steps worth of output because we've said return sequence is true.
But each one is equal to true. What it's doing? Okay,
so basically what it's saying is, the RNN is going to operate on every time step. I mean, there were 50 because the time series had 50 points in it. There were like 50 time steps in there. So what the return sequence says is, for every single time step, give me an output.
Okay.
And if you don't set it, then it'll only give you the output on the very final
one
time. Yeah.
Okay.
So in this case, it will give you 50 pieces of data back because there were 50 time steps in the time series.
Yeah.
And each one of those will be of dimension 20 because we've said that the RNN hidden state dimension is 20. So 50 values, but each one of them of dimension 20.
So vector. So for each value, we're going to have a vector of 20.
That's right. Yes. So at time step 0, value of 20, time step 1, 20, time step 3, all the way up to time step 50, 20. Yeah.
And this vector of 20 is nothing but 20 different weights or hidden states.
It's not the weights. It's so the weights are hidden within the RNN. This is the output. So I mean, this is what the output would be.
Like features in CNN, in convolutional network, you can have multiple features, and here you can have multiple values corresponding to this input. So that's an inner representation of the hidden state, which a network uses.
Yeah. Okay. Got it. So then we could come to the next stage. It's the same, the vector of 20.
Yeah. So the input now here is a bit more complicated in that the input is 50 by 20 because it was 50 by 1 here, but now it's 50 comes in here.
Yeah.
but we haven't told you what the shape is, so it kind of knows from the way it's hooked up. But the
Yeah.
output for us is still 50 values, but each of dimension 20.
20 vector, yeah.
Yeah. And then finally with this one, because we haven't set return sequence is true, it's only going to give us one value back, which is the very final one.
Is it going to give you the one value out of 50, or it's going to give you all 50 value with the vector of 1?
No, it's just going to give you the very final value that it would have computed. I mean, these guys give you all the intermediate ones because we've set return sequence.
Okay, so if it's going to give you the final value, what's the dimension of the value?
You've told it it's going to be 1. It's going to be 1 dimension. So that one is telling it what the dimension of the output is, and it's implicit that you want the last one because you haven't told it this thing.
And that's what I'm saying. He didn't explain it like in order, because if you move to the next example, it would be, I think, a clear, like more clear in like stepwise way to understand the procedure. Okay, let's move on to the next one.
So this one is where what he's doing. So he's taking. So this one it was all neural networks. Sorry, it was all RNNs. Yeah. So there was 3 sets of simple RNNs. Yeah. Whereas now what he's done is he's used 2 RNNs, but then a final dense layer. Okay, so let's look at what the data sizes would be. So we've got 50 by 1. We're returning sequences true, so we return 50 pieces of data of dimension 20. And now here we're going to return something of dimension 20, but we only want the final one because we haven't said return sequence is true. And then finally we have a dense layer, which is just going to give us 1 output. So the output of that would have been 20. Sorry, a single value output, but of 20 dimensions would have come out from that guy. And then that 20-dimensional one would have been reduced to 1 dimension by this dense layer. Does that make sense, Dinesh, that we're going?
Okay, so on a second stage now, this is slightly different, where we are not saying a return sequence is equal to true.
Yeah, so we're only going to get 1 value back.
No, on a second layer, simple RNN.
Yeah, this guy, we're only going to get 1 value back, but it will be of dimension 20.
Okay.
And that 1 value will be kind of like the final one they computed. You know, this RNN is going to go through all the different time steps. It's that final time step that it will give back, and it will be of dimension 20.
Yeah, if you think of this 2-layer RNN as encoder, it takes a sequence of 50 time steps and encodes it in a single vector, which is of dimension 20, which you can choose this dimension. And then you project this encoding of the sequence into a single value, which is your prediction. Okay. Okay. Yeah. So the vector of a 20 in a central layer, like we can say that's the hidden state of the representation of the input of 50. I'm sorry, 50, which we entered in the first layer.
I'm not sure we can say it's sort of like the hidden state. We have to be a bit careful with that, but the output of the simple RNN 20 is somehow kind of giving you those 20 features that will then help you classify, you know, using that dense layer. Okay. Because there's you know, inside the simple RNN, there's those weight matrices, and that's where really the hidden state is. Yeah. You know, it's the weight matrices that are like, you know, are well, in kind of combination with some of these things. Yeah. Although, mind you, I suppose, yeah, I mean, this is, yeah, I suppose it is a certain type of state. Yeah, some of these terms, they're a little bit confusing because.
Yeah, but this is the representation of those input shape or input values which we have given. So yes, squeezed, as Arto said, this is the feature which which is like squeezed down to just a vector of 20.
Yeah.
Yeah.
I guess maybe we can call it hidden state because if we had another RNN, we could have passed that forward onto it. Yeah, maybe it is right to call it. This is the hidden state, but it's a strange term for it.
Yeah. So what's the difference between when we pass the third layer as a dense here, but before we were doing a simple RNN one?
So again, I mean, if you imagine how many parameters there are in here, so I mean, because this is taking dimension 20 to 1, there's going to be 20 parameters.
Yes.
Whereas with the simple RNN, there was only 3 parameters, because the simple RNN's only got how many parameters is that going to have? It's taking an input dimension of 20, and that's going to feed through to a weight matrix of, so I guess that'll have 20 values in that weight matrix. So there must be 20 parameters in there plus a bias.
The 20 parameters plus a single weight for a hidden state, because we have a hidden state of dimension 1 and bias.
Yeah,
and
so it's 23.
22 parameters.
Yeah, so in terms of the number of parameters, it seems quite similar, because this guy's the output of that is 20, and this is a dense layer. Yeah, that's interesting.
Is that in the second case, like a job to summarize this sequence into a single vector, output vector, is on this second simple RNN. And this second simple RNN has much more parameters, because it has 20 by 20 weight matrix from input to like hidden state, and from 20 by 20 from hidden state to hidden state, and also 20 bias.
But even the previous one had that. I mean, okay, we were
here to summarize this sequence. The job was on this last simple RNN.
Yeah.
And it had to encode each of the outputs of the second RNN into a single value, and then take the second output of the second RNN and combine it somehow with its single valued hidden state, and produce the second state and propagate it through this 50 time steps to produce a single output in the end. And in the second case, it is slightly different, because this second RNN layer does that.
Okay.
Combines all the steps into is responsible for producing, encoding all the sequence into single output.
Yeah, it's interesting. Yeah.
Yeah, but in terms of number of parameters, those two models are similar, I think.
It just must be the way, because this is returning 50 values, and that's simple RNN. The way that's working, because it's only got a hidden state dimension of only 1. It's rolling it across the 20, even though the inputs are of size 20. You're quite right. That hidden state just does not have a lot of information. Whereas in this case, we've got something with 20 features, and then we've got potentially 20 parameters to work across all of those features to compute a final output. Although I mean, it's not 100% clear, but yeah.
A wrong way about explaining this, because the first thing I would do, I would add this final projection, a dense layer, and increase the number of hidden states in the single layer RNN, and evaluate that, and then add an extra layer, because he starts with making this RNN multi-layer before even trying to make single layer RNN work well.
Yeah. Yeah, no, yeah, I agree. I mean, I guess he was just trying to prove that, well, I think his main thing here is that the performance of this, not only is the, you're getting quite good performance in terms of the output, but actually this is quite quick as well. Because RNN, because of the way they internally work, they're kind of like iterative, where this is kind of like a much more simpler matrix multiplication here that's happening. Yeah. And you can change the output activation function as well. So we're at about 10 to 8. So let's really look as to, okay. Let's have a little look. I think it might be worth leaving this because this is quite involved actually. If the guys cover it tonight, then maybe next week we'll redo this bit right at the beginning before we get on to the rest of it. Although actually they're only doing this until Sunday, aren't we? There's only 2 days for this. Let me just check that we've only got 2 sessions for this one.
I don't think they're gonna go that far. They usually go very slow and a lot of this.
Yeah, I mean the next section is actually I remember reading it and finding it quite tricky. Yeah, they're only doing. Potentially, we have got some time, in the holidays. Yeah.
Next Wednesday, we can like they have a holiday. Oh, there are 3 holidays. Yeah.
Yeah. So next Wednesday is before Christmas Eve, even. So in theory, we could do it.
Yeah, let's meet next Wednesday, definitely.
Yeah, let's see how they do on Sunday. And if they're already covered that bit, because as I said, I found it a bit hard to follow that one because the matrices were getting quite complicated. And he had like a few different variations where you were predicting 10 steps ahead and feeding data in various different ways, which was making it all a bit tricky. Okay, cool. Yeah, let's see how we get along. And then we might meet next Wednesday to go through this bit if they already do it.
All right.
Okay, thanks guys.
Okay, thank you. Thanks.
Yeah, right. Speak to